Hello. Today we are going to move to the next section 10.5. This section is rooted trees. Since this section is little longer, I'm going to break this section into two parts. Today I'm going to teach the first part. In the next day I'm going to teach the next part. This is chapter 10, Theory of Graphs and Trees. In the last section, we learn about trees, trees in general. Now we're going to learn about a specific type of trees. Those are called rooted trees. All right. So let's move forward. In mathematics, a rooted tree is a tree in which one vertex has been distinguished from the others and is designated the root. Okay, rooted trees are the trees which are having a specific vertex which is called the root. Okay, so this can be the root and then the subsequent vertices like this. Okay, so this is a rooted tree. This has the root. This can be denoted as the root. All right, those are the rooted trees. That's a specific type of trees. In general, trees are not, the roots are not specified in a general tree. But in rooted trees, we just specify what the root is. Okay, so that's the difference between rooted tree and a general tree. Given any other vertex V in the tree, there's a unique path from the root to V. Okay, let's say there's a vertex V in this graph, in this tree. Let's say this is V. There should be a specific path to V from the root. That specific path can be given like that. All right, there's a specific path for any given vertex from the root. All right, there's a unique path from the root to V. There's a unique path from the root to V. The number of edges in such a path is called the level of V. Okay, so here if you just consider the yellow path, this is the first edge, second edge, third edge. Okay, there are three edges from root to the V. Then that is called the level. Okay, the level of V is three edges. Okay, it has three edges. Okay, so then and the height of the tree is the length of the longest such path. The height is known as the length of the longest such path. Okay, length of the longest such path. In this graph, the height of the longest path is 3. So the height of the graph is 3. Okay, for this graph, length of the longest path I'm sorry. The length of the longest path is 3. Thus, height is 3. Okay, the height of this graph is 3. All right, the height is the length of the longest path. It is traditional in drawing rooted tree is to place the root at the top. We normally place the root at the top and show the branches descending from it, and then the branches are just descending from it, like I have drawn right here. Okay, like that. All right, so let's move to the next slide. A rooted tree is a tree in which there's one vertex that is distinguished from the others and is called the root. So these are the definitions. Okay, for a rooted tree, there should be one vertex that is distinguished from the others. This is called the root. All right, so you have learned the root. The level of a vertex is the number of edges along the unique path between the root. Then if you want to check the level of a vertex, that is the number of edges along the unique path between it and the root. I have just shown this early. All right, I have just shown this early. The level is 3 in the previous case. The height of a rooted tree is the maximum level of any vertex of the tree. That's the maximum level of any vertex of the tree. In the previous graph, the height was 3. All right, let me draw another example if you need another example. So let's say this is the root. There are, let's say, 3 vertices, and here 2 vertices, 1 vertex, 2 vertices, 2 vertices, 2 vertices, and then here 1 vertex. So this is a rooted tree. If you consider this as V, the level of V is number of edges when you get into V from the root. So this is the root. When you want to get into V from the root, so this is the path you follow. So the level of V is V is 2. All right, in the next case, and the height of this tree is the largest level, the longest level for any vertex. Let's say this is V1, and the level of V1 is 2, and then let's say this is V2, and then the path should look like this. Okay, the path should look like that. So just count the length. Previously it was 1, 2. Now the length is 1, 2, 3, 4. Okay, that's the height. Height of the tree is 4. All right. Then given the root or any internal vertex of V of a rooted tree, the children of V are all those vertices that are adjacent to V and are one level further away from the root than V. Okay, now we are going to talk about children of a vertex. Okay, let me read it again. Given the root or any internal vertex of V, we have to get an internal vertex, any internal vertex. Let's say this is the internal vertex that I am interested of. Maybe this one, V3, the internal vertex. The children of V3 are those vertices that are adjacent to V and are one level further away from the root than V. That means we have to go one level down, one level away than the root. V means we have to go down. We have to go away from the root. That means we are going down from V3. Okay, so these are the children in that case. These are the children of V3. Okay, let me mark it here. Let me mark them as V4, V5, V4 and V5 are children of V3. All right. So V4 and V5 are children of V3. And then go forward. Then we are going to talk about parents. If W is a child of V, then V is called the parents of W. And two distinct vertices that are both children of the same parents called siblings, like a family. Okay, now just talk about the parents. If W is a child of V, then V is called the parent of W. That means this is the parent of V3 is parent of V4 and V5. All right. V3 is parent of V4 and V5. All right, then we're going to talk about siblings. Two distinct vertices that are both children of the same parent are called siblings. Okay, that means if you consider again V4 and V5, they are siblings. All right, let me write it here. V4 and V5 are siblings. Okay, they are siblings. Then given two distinct vertices V and W, if V lies on the unique path between W and the root, then V is an ancestor. Ancestor of W. That means, let me check which ancestors. If you consider these two, V3 and V2, all right, V3 is an ancestor of V2, all right. All the vertices above a given vertex can be called ancestors. Okay, all the vertices above a given vertex is known as ancestors. All right, in that case, V3 is an ancestor of V2. Okay, at the same time, the descends. Okay, the reverse of ancestors is descends. All right, at the same time, you could say V2 is a descendant of V3. Spelling is wrong. Let me correct that. Is a descendant of V3. All right. So now you know everything about parents, children, siblings, descendants, ancestors, and everything. Height of a tree, and then what are rooted trees and everything. So this slide gives all the definitions about rooted trees. Okay, so let's go to the next slide. There's an example of a rooted tree. These terms are illustrated in figure 10.5.1. That means the terms that we learned early are illustrated in this slide. First of all, let me try to delete this extra slide. Give me a second. I will quickly do this. All right, let's go forward. It is right here. All right, we have an example. Now you know in this tree, levels are also marked. This is level 0 where the root is located, and level 1, level 2, level 3, level 4. There are 4 levels. All right, and then there's the root, which is kind of the top of the tree. That is the root. Okay, and then we marked U here. All right, and then what we do, we just consider this part of the, let me use a different color. We just consider that part of the tree. Okay, that part of the tree. This part, all the vertices in this part are descendants of U. Okay, are descendants of U. Okay, all those are descendants of u. That means after u exist, or every other vertices below here became exist. So that means they are descendants. All right. And you see that u is a child of v is a child of u, v here, u there. All right. And u is parent of v, that's true. V, W are siblings. These are siblings. All right. So this example is good. It explains most of the technical terms that we discussed early. All right. So this is a rooted tree. Just go to the next slide. In this slide, we're gonna discuss an example. All right. Example 10.5.1 rooted tree. Consider the tree with root v naught, which is right here, shown below. So there are several questions you have to answer. What is the level of v5? Okay, first of all, you have to find what v5 is. v5 is right here. Okay, so to reach v5 from v0, so you have to go like that, and then you have to go like that. Okay, this is the first edge, that is the second edge. Okay, the level of v5 is 2. There are 2 levels. Okay, what is the level of v0? v0 is right here. v0 is right here. So no level for that. That means level 0. That is the start. Okay, that's level 0. What is the height of this rooted tree? What's the height? For the height, you have to measure the largest level of this tree. Okay, the largest level. You can see the level of this vertex is just 1, 2, 3. Level of that vertex is also 3. 1, 2, 3. Level of this vertex is also 3. 1, 2, 3. And level of that vertex is also 3. Okay. There are a lot of vertices with level 3. So that is the maximum height of this tree. Okay, that's the maximum height of this tree. So the height of the tree is just the length of the largest level. You could say it is 4. You could choose anything you would like. This, that, or that. All are having level 4. Let me write it here. Level equal 4. Level equal 4. The height of this rooted tree is 4. What are the children of V3? Just find V3. All right. So the children of V3 are this and that. Children are V5 and V6. Oops, sorry, what's going on? Okay, V5 and V6. And then what is the parent of V2? This is V2. The parent of V2 is V0. It is V0. What are the siblings of V8? V8, that is right here. What are the siblings of that? There are two siblings of 4V8. The first sibling is right here, the other sibling is right there. All right, so because they all are having the same parent. The common parent for all these three vertices is just V4. Siblings are V7 and V9. What are the descendants of V3? Yes, V3. Here V3. The descendants of V3 are the vertices that are just below V3. Okay, that are just below V3. They are V5, V6, V10. V5, V6 and V10. V5, V6, V10. How many leaves are on the tree? Leaves are the terminal nodes. You have to count how many terminal nodes are there. This is a terminal node, that's a terminal node, this is a terminal node, terminal node, terminal node. There are 5, let me count. Okay, there are 6 terminal nodes. Okay, there are 6 terminal nodes. Terminal nodes are leaves. Okay, terminal nodes do not have children. They do not have children. Okay, so those are the answers for this example. Let's move to the next slide. In the next slide, we are going to talk about binary trees. All right, binary trees. Binary trees are a special type of rooted tree. Okay, a special type of rooted tree. We can understand what are binary trees very soon. When every vertex in a rooted tree has at most 2 children, and each child is designated either the left child or the right child, the result is a binary tree. Okay, so this is the definition of a binary tree. It's a rooted tree has at most 2 children. It should have only at most 2 children. So it can have 1 child or 2 children. All right. Each child is designated either these children are either left child or the right child. Okay, so you can just designate this is the left child, that's the right child, or maybe only left child, or maybe only right child. All right, so this is called a binary tree. If I draw a binary tree, it should look like this. Here there are 2 vertices, again 2 vertices, and here again 1 vertex. This is a binary tree. This is a binary tree. All right. And then let me draw something else here. One node there, 1 node there, and 1 node here, 1 node here. This is not a binary tree because this has 3 children, not a binary tree. All right, now you understand what are binary trees. All right. Here we have definition. There are several definitions in this definition. Let me read. A binary tree is a rooted tree in which every parent has at most two children. Okay, has at most two children. Each child in a binary tree is designated either left child or right child. You could say this is right child. All right, so here you could say this is left child, that is right child. All right, that's great. Okay, go down. Okay, you know what is the left child, what is the right child. And every parent has at most one left child and one right, at most one left child and one right child. It doesn't matter, you don't either, you don't have right child or left child. It can happen, right? So at most means the maximum is one right child and one left child, but we don't care whether they have right child or not. That's not important. A full binary tree is a binary tree in which each parent has exactly two children. Now this is a special type of binary tree. That means it has exactly two children every time. Okay, so this is a full binary tree. I'm sorry. Vertex here, vertex there, vertex there, vertex there, vertex there. This is a full binary tree. Every parent has two children. This is a full binary tree. Okay, it's a full binary tree. All right. Given any parent v in a binary tree T, if v has left child, then left subtree of v is the binary tree whose root is left child of v. All right, let me explain this using a different diagram right here. Give me a second. All right, this is explained right here. Let's say you have a tree like this, one vertex here, two vertices like that. Okay, let's consider this tree. Now I'm going to explain this block. Given any parent v in a binary tree, let's say this is v. If v has left child, of course it has left child. This is the left child. V has the left child. Then the left subtree of v, which is this, This is the left subtree. Left subtree right here of V is the binary tree whose root is the left child of. So if you just consider this green part, for this green part, this is the root. Alright, so this is the root for the green part. The root for the green. Okay, so green sub, let me just complete it. Green subgraph. Root for the green subtree. Alright, that's given right here. Alright, so that's how we define the left subtree of V. Let me read this again. Given any parent V in a binary tree T, if V has left a child, then the left subtree of V is the binary tree whose root is the left child of V, whose vertices consist of the left child of V and all its descendants. Okay, all its descendants. And whose edges consist of all those edges of T that connect the vertices of the left subtree. Okay, that's how you define the left subtree of V. And the right subtree of V is just a single node. Let me just expand that little bit. Let me just modify this tree a little bit. So what I'm going to do is let me delete that too. That's the left subtree, and then I'm going to add more vertices here like that, like this, like that, like this, like that. Okay, so that's the left subtree, and then this is the right subtree. Already the right subtree. Where's the pink? This is the right subtree. This is the left subtree. All right, you know about subtrees now. All right, so let's move to the next slide. Now again, you have a binary tree as an example. So this example explains everything. It has the root right here. All right, and the root has two children, U and W, and U has V as the left child. Okay, so this is the left child of U. Okay, v is the left child of q. And then here you have w, and w has two subtrees, subtree number 1 and subtree number 2. These subtrees are left subtree and right subtree. Okay, left subtree and right subtree. Left subtree of w, right subtree of w. Alright, so this is the x is the child of w. This I explained this in the previous slide. Alright, just go further down. Binary trees are used in many ways in computer science. In this class, there are a lot of computer science students. You guys know about binary trees. This is an example where you use binary trees in computations. One use is to represent algebraic expressions. You could represent algebraic expressions by binary tree. All right, with arbitrary nesting of balanced parentheses. Okay, so there are arbitrary nesting of balanced parentheses. All right, let's explain very soon. There's an example where I can explain that. For instance, the following binary tree represents the expression a divided by b. The operator is at the root. The operator is at the root, which is right this. And act on the left and right children. So this is the left child and that is the right child. All right, so that is an algebraic expression given as a tree. Okay, so how do you write this? You write a divided by b. The order is important. The order here is left to right order. Left to right. Okay, you start from left. That is left. And this is, you have to go from left to right. You have to start from left, go up, go right. That means go down. That is a divided by b. Give me a second. All right, let's go forward. All right, we have an example, another example, example 10.5.2, representation of algebraic expressions. More generally, the binary tree shows below represent the expression a divided by c plus d. Okay, a divided by c plus d. So first of all, you have to recognize what are the operators here. There are two operators. Okay, those operators are division and summation. These operators, and these are variables. Variables are a, c, and d are variables. Okay, so let me read this. In such a representation, the internal vertices are arithmetic operations. Okay, so these are the internal vertices. They are always arithmetic operations. Internal vertex, they are internal. Internal vertices are arithmetic operations, and leaves are variables. Leaves are variables. Leaf, leaf. Those are the leaves. Okay, leaves are variables. And the operator at each vertex acts on its left and write subtrees in left to right order. Order is important. Left to right order. You start from the leftmost node. Left, go up, go down. All right. And then start from here, go up, go down. Okay. This is the way you write this. First of all, you have to start from the bottom of the tree. So this is the bottom. Just write that one. This is C plus D. All right. And then you just combine this green part to the rest. Okay. Then you just how do I do it? Let me do like this. Then you consider this along with C plus D. Let me rearrange that. And then this graph will become something like this. That operator, this operator, and then C plus D. You could put C plus D into one vertex because we have already computed that. And then the answer for this one should be A divided by C plus D. All right, which is given to you. All right, good. Now there's another tree given to you. This is this seems to be a big tree. Let's put this algebraic expression in a tree. All right. This expression I am gonna just split this expression into branches of the tree. So the given expression is this. A minus B times C plus D divided by A. So I can clearly see that this is separated from that. Okay, so in this expression I can clearly see that these two parts are separated, can be separated. So that means this can be represented by one branch. Let's say branch number 1, branch number 2. So this can be represented by the branch number 1. Maybe I would say subtree. Subtree 1. Subtree 2. All right. So first of all, let me mark that. Subtree 1 and subtree 2. And then you can still see subtree 1 is still complicated. Okay, so let me write that down. A minus B times C, which is still complicated. So I can represent that one like this. I'm going to split that into another two pieces. This separately, that separately. And then this is I would say subtree 3. This is subtree 4. All right, so that way I split this expression into 4 subtrees. Now I can easily draw that. So first I had to work on subtree 1 and subtree 2. So this is my root. My root should represent this, the summation. Okay, and then it has 2 branches. One branch goes like that, the other branch goes like that. All right. In this branch, I have another 2 nodes or the vertices. So this is division, that is D and E. This is D and this is E. Alright, so that is this part. This part is that. Alright, so that is first subtree, and then in the next subtree I have to represent multiplication here, and then it has two sub branches. So this is definitely C, and here this is negative, that is A, that is B. Alright, so let me mark this in that color. So that is that. And then C is right here. Let me mark C in a different color. That is C. Alright, and then this entire thing is that. Okay, so that is the expression. So this is the complete expression. Alright, so let's move to the next slide. Now we are going to talk about a theorem. This is a very important theorem. Let me read this first. An interesting theorem about full binary tree says that if you know the number of internal vertices, if you know the number of internal vertices, then you can calculate total number of vertices and the number of leaves. All right, you can compute a total number of vertices and the number of leaves if you know the total number of internal vertices. So that theorem given right here. If k is a positive integer and t is a full binary tree with k internal vertices, then t has total this many vertices and that many leaves. Let me discuss one quick example. Let's say you have a tree like this. This is the root, that is that is that. Sorry. All right. So here how many internal vertices? Let me count. 1, 2, 3. There are 3 internal vertices. Let me add more vertices. There are 4 internal vertices in that case, right? 1, 2, 3, 4. There are 4 internal vertices, okay? 4 internal vertices. Then if you know how many number of internal vertices there, then you can find how many total number of vertices and how many leaves in this tree. All right, that means k equals 4. That will give you total number of vertices, which equals 2k plus 1, which is 2 times, that is 9. There are 9 total vertices. Let me count. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. That is correct, right? It is 9. And then it says number of leaves. total number of leaves equals k plus 1. That is 4 plus 1 equals 5. Let me count. This is a leaf. 1. This is a leaf. This is a leaf. This is a leaf. That's a leaf. There are 5 leaves in this tree. All right. So the theorem is true. You can see that. In the next day, we're going to prove this theorem. Since you don't have time today, so next day we are going to prove this theorem. That's all for today. Thank you very much.